Okay, welcome everyone to the Applied Topology Seminar. The speaker today is Omer Bobrowski, and he will tell us about homological percolation and the formation of giant cycles.
Thank you, Sarah, for the introduction and for the invitation to speak here. So this is, first of all, it's a joint work with Primož Skraba from Queen Mary University. Sort of on the border between TDA and probability. This is not working, just a second. Okay, so I'm going to start with trying to give you two angles of motivations for this work. One which is more TDA flavored from persistent homology, and the other one is from probability theory related to percolation theory. Then I'm going to describe to you the main setup and results that we have so far. Another part of this work is about some weird connection or unexpected connection to the Euler characteristics that we sort of found, and I'll present that at the end. So I'm going to start with the motivation. When you have persistent homology, basically what we have is a filtration. We have an increasing sequence of spaces. And if we think about a geometric complex built on top of them, then we can produce this barcode, tells us which cycles we have, each of them with the birth and death times. And sort of the common practice is to say that the long cycles are the significant features in the data. Like here we have the annulus or the circle with the big cycle that it produces. And also we have lots of small cycles representing those noisy cycles, if you want, things that we might or might not want to ignore. We might think of the big cycles as the signal, the important information that is hiding underneath the data, and the small cycles to be the noise, the things that we don't want to see or we want to ignore somehow. And this is very a heuristic thing to say long is important, short is not important. The question many people are trying to answer is the way to make this more rigorous, to have some statistical difference between signals and noise in those persistent diagrams, and a way to differentiate between cycles. Now, along these lines of the probabilistic analysis, we have an old result related to the largest cycles that you can see in a noisy setting. So if you don't have any signal, if you want, only noise, how large can the largest cycle be? And here we have the following result. So suppose that you have IID samples, just points in some nice space. And we measure persistence not by the length of the bar, but rather by the ratio between the death and birth for various reasons. And we measure the maximal cycles among all the noisy ones, meaning not any cycle that is related to the underlying space, but just a small noisy one. And the theorem that we have is that if we take the size of the largest cycle, which is random, we cannot say much about it yet, but we know the order of magnitude. And the order of magnitude scales like log n divided by log n to a power that depends on k, where k is the dimension of homology. This is work with Matt Kale and Primož Skraba from 2017. So it gives you some measure to how big a cycle can be if it's coming from the noise part. And now possible question to ask is, how does this compare to the signal cycle, to the true cycle that we want to recover? Now, for those cycles, what we know is that the death time doesn't change with the number of points. It's just a feature of the underlying manifold of space. If you want the filling radius or the condition number or something like that, that determines how large a cycle is. It doesn't depend on your sample. So if you want to know this ratio between death and birth, you need to say something about the birth time of those cycles. And this is sort of the starting point, or the TDA starting point of this work. If we have persistent homology calculated over point sample that is coming from some manifold, when does the large cycles, what time they are created? At what radius exactly do we see them for the first time? So this is the motivation from this work from the TDA perspective.
Omer, could I ask a
yes.
naive question?
Yes.
So if you just go back to the last slide, so this pi k of n, I'm not good with logs, but as n is getting larger, this is also getting larger. Is that right?
Correct. Yes,
And
because
so,
we're taking the ratio.
it's because we're taking the ratio. I see. So
So
like
you can have cycles that are created much earlier, but then last for a lot longer, and even though the death and
right.
the birth are finite, I mean the ratio explodes. And the question is how it's going to happen in the true cycle as well. But the question is how do they compare?
Right. Thank you.
Okay, no problem. All right. So moving on to the probabilistic angle. This is coming from percolation theory. So this picture sort of explains in the words what percolation is: slow passage of liquid through filtering medium. So if you have this cycle of water, here is the part of the percolation where the water percolates through the dense through the ground, and so there's some dense medium through which the water molecule has to go through, and basically we want to know if the water has a way to go through this medium and go down to through this cycle. And basically the way we can think about it is we have some condensed material, and we want to see if there is a crossing path that the water can flow from one side to the other. Or in a way, we want to ask questions about big connected components such that the water can flow throughout them. And this is the idea for the study of percolation, or at least sort of the statistical physics and motivation for it. And there have been several models in the mathematical literature, quite old by now, from the 60s, more or less, for percolation. The very first one is the bond percolation model by Broland and Hammersley. And the model goes like that. You have an infinite grid, and what you do is for each edge, you flip a coin and you decide whether it's open or closed. So open will be black, and closed means that there is no flow through it, will be gray. And now you mark one point, the origin, for example, and you look at the connected components that connect to the origin. And the question you want to ask is this connected component, which I call C0, is it infinite? Throughout this grid, does it go all the way to infinity, or is it something local? So that's sort of is the fundamental question in percolation theory. Like a lot of things in mathematics and in probability in particular, they started with some infinite limiting object rather than a local one, but we'll see local questions as well in a second. There are other models also popular, the SITE-PERCOLATION model. It's quite similar. You still look at the infinite grid, but now the random part is not on the edges, but rather on the vertices. So each vertex can be open or closed. So we remove some of the vertices from the grid, and now we connect the rest of them along the grid lines, and we ask the same question: is the origin connected to an infinite component or not? So these are the most well-studied models in percolation theory. Another quite popular model is the continuum percolation. This is the one that I'm going to look at in this talk. Also quite old by now. Here the randomness is more geometric in the sense that the randomness is in the points. So it's no longer a grid. We have this collection of points. They can be randomly located in the space. And the way we connect them is by distances, or by drawing balls and looking at the components generated by the union of the balls. And again, we ask the same question. We look at the connected component on which the origin lies, and we ask, is it infinite or not? So these are three different percolation models, although the general phenomena is quite the same between them. Just the proofs could be different, the quantities can be different, and generally the behavior is as follows. So there's some model parameter. It can be the probability to see for a site to be open or closed, or it can be the rate of the Poisson process, how many points do I put in. And there is some, we can define theta to be the percolation theory. So for a given parameter value, what is the probability that the origin is connected to infinity? And then there is a critical value. So at the beginning, if the parameter value is very low, the structure you have is very sparse, and the origin is not connected to infinity. But as you increase it, at some point, you expect the probability to become positive. So it looks something like that. This is for bond percolation, for example. You start with probability 0, and then you need to hit a certain probability to be able to see infinite components with some positive probability. And then it increases all the way to 1 at the end. Now you can change the question a little bit. Here we ask sort of whether the origin is connected to infinity or not. You can ask a different question, which is there an infinite component anywhere? Not necessarily at the origin, but anywhere in the grid or anywhere in the Euclidean space. And then the probability behaves has a sharp phase transition. It's either 0 and 1. There couldn't be anything in between. And if we're above this critical value that I just defined to you, then not necessarily the origin is connected to infinity, but somewhere there is an infinite component. And if you're below that, then nowhere is there an infinite component. And moreover, if there is an infinite component, there's only one. There could be two infinite components somehow lying in two different areas. There's only one, and it goes out sort of everywhere. It sends arms everywhere. And this typical behavior is true for most percolation models, especially for the three ones that I described to you before.
And Omer, when lambda is, in that last question, when lambda is equal to lambda c, is the probability usually either 0 or 1, or is that an interesting question?
So that's actually a pretty difficult question to answer. In most models, it's not known what happened exactly at criticality. It's easier to prove what happens below and above. At criticality, it's hard, and it's different between the models. Okay, so far we discussed about this infinite event. We want to work with more local questions, and percolation theory deals with that as well. And instead of looking at the infinite grid, what we're going to do is we're going to look at the local area, which is a box in this case. So we take the same model, the infinite grid, but just a slice of it, just a box. And instead of asking for an infinite component, sort of an equivalent or at least something which is intuitively similar is to ask whether there's a path that crosses the box from one side to the other. Because we expect if there is an infinite component, it should be easy to cross the box from one side to the other, and otherwise maybe not. So this is another important question in probability theory about these crossings. So we want to ask for a path that can cross the box. And again, the behavior here is quite similar between the models, and it goes as follows. So let's say we're taking a box with dimensions that scale like n, but maybe with different proportions. So we allow the boxes to have slightly different proportions, but they all somehow depend on this parameter n that we're going to increase. And we can define crossing events. Either we can ask whether there exists a crossing in one of the directions, or do we have all the crossings in all the directions? Turns out that it doesn't matter. The answer will be the same. So in this picture, for example, you can ask whether you only have the red crossing or both the red and the blue. And here there is a limiting phase transition. So if you take n, the box to be larger and larger, what you can show is that you can look at the same critical value we had before. If you're above the critical value, then the probability goes to 1 to see all the crossing components. And if you're below the threshold, then you can show that the limit is 0 to see any of the crossing components. So either you have all of them or you have none of them with high probability. Okay, moreover, those crossing, all the crossing paths belong to the same component inside the box, which we will call the giant component. Okay. So basically, there is above the threshold, there's one big component that produces crossing paths in all directions. Now, just an observation that I will use in a second. What I did here, if you think about the example with the balls, so I placed balls with fixed radius, and I take a box which is growing bigger and bigger. Instead, what I can do is I can fix the size of the box and just make the balls get smaller and smaller. It's an equivalent model, but for us, it will be a little bit easier to think of it this way. Okay, so this is again the general behavior for crossing paths in percolation theory. So again, I want to work with the continuum percolation model, so let's be a bit more precise. What we will think of is we have, again, IID sample. So we have a Poisson process, which is constructed in the following way. We generate a sequence of points IID, let's say in the cube. We choose a random number from the Poisson distribution, and then we take the first big N points from this sample. So this thing is called the Poisson process's rate N. On average, it has N points, but it could be a little bit more, a little bit less. And the points are spread in an IID fashion uniform. So I look at the box and I have some setup of points. Now in the continuum percolation model, we can consider two different sets. The first one we'll call the occupancy. which is just a union of the balls that we saw before. But we can also look at the complement, which we're going to call the vacancy. So it's everything that is not including in those points. And this is this yellow region. And both of them have some interesting random behavior, and we can ask all the questions related to probability on both of them. So tell that for this model, there is the percolation phenomena appears in something which is called the thermodynamic limit, which basically tells you what is the connection. So here, as I said before, I'm going to keep the size of the box fixed, but the radius is going to get smaller. And it has to get smaller in a very specific way so that n, the number of points, times the radius to the d. Do you see my pointer? Yeah? Okay.
Yeah, we can see
so
that.
N times R, cool. So n times r to the d has to be a fixed number, lambda. And the lambda will be our parameter that we're going to play with. So this is called the thermodynamic limit. If we increase lambda, basically we have a denser and denser structure. Now, notice just a comment that the threshold where percolation appears, it's much earlier than other phenomena. Like if we ask when does this the union of the balls become connected, or when do we have coverage of the entire box, this happens much later when the same term n r to the d is Cech log n, so it's getting bigger. So we do not expect things to be connected or covered. It's a different picture. And the picture looks like that. So I have this box. I place the random points, and n will be basically how many points I have, and the more points I have, the smaller the radius that I'm going to take. So I have this process where I'm adding more points, and when I do that, I'm reducing the radius. And as you can see, I'm getting something that is sort of getting more and more complicated, but it's not dense enough to cover everything, and it certainly doesn't have to be connected. And we can imagine that there's all sorts of cycles being created here. And this is the kind of object that we want to look at. Okay. So what is known about this continuum percolation model? So here we know that since we have two objects, we have the occupancy and the vacancy, the balls and the complement, we also have two different thresholds. Call them lambda and lambda bar. And the picture sort of looks like that. So we have, if we look at the occupancy process, the balls, then we have lambda c, the critical value. And if we're above this, then we can say that there is a unique giant component like before, and we can cross the box in all the directions. So that's everything to the right of the critical value. And if we're below that, then all the components are small. We cannot cross the box. Nothing big happens. The same thing happens to the vacancy, but in a different direction. Okay, so in the vacancy process, the complement, if the rate is small enough, then the vacancy is big enough, and then we have all the things that we want. We have a giant component with all the crossing, etc. And if lambda is too big, then the vacancy, the complement is too small, and then we don't see anything. So here we have sort of two thresholds, and things do not have to coincide. So we can have a range of values where we have giant components both in the occupancy and in the vacancy. In 2 dimensions, it doesn't happen. So in 2 dimensions, both thresholds are the same, and we do not have that. But for higher dimensions, they can live together, they can coexist. And that's how it is in the continuum percolation model. Okay, so this is what is known about those crossing paths in continuum percolation models. And sort of this is the starting point for the work that I want to tell you. And what we wanted to ask is there some, so we're talking about connected components all the time, is there some higher dimensional notion of this percolation phenomena that can somehow relate to homology, which is the higher dimensional generalization of connected components in a way. And the idea we had is the following. So suppose that I'm changing the model a little bit. I'm generating this Poisson process, not in a single box, but I have a union of two disjoint boxes, and I place both points in both of them and do the same thing. In this case, if the parameter value is large enough, I do not expect to see a unique component, but I expect to see two giant components, each of them producing a crossing path for each of the box separately. They will not connect. So in a way, the giant component, what it tells us is something about the components of the underlying space or of the support of the distribution. The number of components we have would be the number of the giant components that we have. Or if we want to use a homology language, then we can say that the giant components in continuous percolation tell us something about the non-trivial zero cycle. So our idea was that the generalization to say something, call something a giant K cycle is something that is created in a random structure that is connected to the non-trivial K cycles in the support of the distribution. So in the visual example, suppose that my points are not generated on the box because it doesn't have any non-trivial homology, but on the torus. Then if I somehow manage to create a path that goes on the top of the torus and create this cycle, I'm going to call this cycle a giant cycle because it's a cycle that belongs to the torus. It's part of the homology generated over the torus. Whereas if I have a cycle that just goes on the side of the torus, it's mapped to zero on the torus, and therefore I'm going to consider those as the small cycles. So this is our idea of how to generalize the idea of the notion of giant components to giant cycles. Basically, we want to capture those cycles of the underlying space, which now relates to the motivation I gave you from TDA. We want to find the birth time, right? The first time that those big cycles appear.
Okay. Can I ask a question really quickly?
Of course.
Can you hear me?
Yeah.
Sorry, so I think I just missed in the previous slide what the relationship between the two separate Q spaces. Like, so when you move from talking to the union of two disjoint spaces to the torus, was there a relationship there?
So at the top, what I'm saying is I'm generating this point process on two disjoint boxes, and I'm looking at what happens, and I'm saying that there are going to be two giant components. Now I'm saying instead my model will be it will be more precise in a second, but suppose I'm generating my points not on any boxes, but on a torus. So there, I expect to see one giant component because the torus has one component, but I expect to see two giant cycles because the torus has two cycles. What I'm saying is what I'm looking for is I want to see the cycles of the torus appearing in my random sample. That's basically my definition of a giant cycle.
Okay, yeah, thank you.
Okay, no problem. Any more questions before I proceed? Cool. So I'm now going to make things more precise and tell you what the results are and a little bit about what is required to prove them. So I'm going to narrow down to the nicest model that we can work with, but also it's rich enough to sort of so we can describe what we want. We're going to work with the flat torus, meaning that we're going to take the d-dimensional cube and just put periodic boundary condition on it. So we're generating points basically on a unit box, but when we draw a ball, it comes back from the other side. So this is the model that we're working, which is equivalent to saying that we're just sampling from a torus. And it's nice because the torus has all the cycles in known dimensions, so we can ask for different Ks, when do we see different giant cycles? And it's also mathematically very easy, very nice to work with. We're going to generate a point process on this d-dimensional torus in the same way as I told you before. You pick n points at random. And now I want to make the definition of a giant cycle more precise. So in order to do that, I'm looking at I have an inclusion map from the union of the balls from the occupancy process to the torus. And this induces map in the homology between the homology of the random homology of the union of the balls mapped to the homology of the torus. And my giant cycle are just going to be the image of this map. So everything which is every cycle that I see in my random structure that is mapped to a non-trivial cycle in the torus. So everything like that I'm going to call a giant cycle. And my questions are going to be about this image of I star.
Question, doesn't the ball have null homotopic, so that inclusion map is not going to give you anything? Confused.
But I have a union of balls. I have many balls union together.
Okay.
Huh? Like before. In this picture, you just see one ball, but I'm going to place n goes to infinity points, so it's going to be a lot of them. Okay. So I have this inclusion map from the union of the balls. Yes, BR of Pn is all the balls around all the points in my process. The giant cycle is everything which is non-zero in this image. And what I'm going to call homological percolation is the stage where those cycles appear. So I can define two events. One of them is I can ask whether there exists a giant cycle, which in our language run we ask whether this image is non-zero. Is there any of the cycles of the torus does it appear on in our random sample? And I can also ask, do I have all the giant cycle? In that case, it means whether the image of I star is equal to the homology of the torus, so we have all the cycles. And this question can be phrased for different k. You can ask it for different dimensions. And what we want to ask, like in percolation theory, at what point we change the parameter value, at what point can those probability change from being 0 to being positive? One comment, which is maybe not surprising, if we want to be able to create a giant cycle in this random sample, there needs to be a giant component first, because we want something very big that sort of wraps around. Everything needs to be sort of nicely connected. So the phase transitions that we're going to be studying here is going to appear after the results I was telling you before about the crossing path and all that. The question is when? Okay, so this brings me to the main result, the main theorem that we have. So we have two events. EK would be the event that one of the big cycles, one of the giant cycles appeared, and AK is the event that all of them are already in my structure, which means that we have all the cycles of the torus, but we can have many, many other small cycles that do not belong to the torus, but we want to ignore them. So the theorem looks like that. It's not yet the theorem that we want to have, and I will explain in a second. So we have a sequence of thresholds, which increases by the dimension. So we have a threshold for the one cycle, a threshold for the two cycles, and so on. But we also have two types of thresholds, which we mark as 0 or 1. And what we can show is that above lambda k1, the probability to see all the cycles, all the giant cycle goes to 1. And below this threshold that I call lambda 0k, the probability goes to 0. So this result is not as nice as we want, because before I told you that there's one threshold and it's either 0 or 1. And here what we can prove is that there is a range where it's surely 0, there is a range where it's surely 1, but in between, we don't know exactly what happened.
So you would like to get that lambda 1k and lambda 0k are equal?
That's the conjecture, but it stays a conjecture for now, unfortunately. Yes. So a few remarks about this theorem. So first of all, the lambda parameter is what equals n times r to the d, and the number of points are the radius of the balls. So together they give you lambda, and this is the value that appears, and this is the thermodynamic limit I was telling you about. So it's in the same limit as the regular percolation phenomena I was telling you before, just the values here are going to be maybe after. There is a nice ordering to the threshold. So first of all, we see the giant one cycle, then we see the giant two cycles, then we see the giant three cycles, and so on. So there's a nice ordering, which a priori doesn't have to be. What we do know is that for the top and bottom dimensions, so for lambda 1 and lambda d minus 1, the threshold coincide, and we have a sharp phase transition. So we have one threshold value, which is actually coincides with the threshold we had before for crossing paths. So when we have crossings, we also have all the one cycles. And on the other hand, when we have crossings in the vacancy, in the complement process, then that's the point where we have all the d minus 1 cycles. So those are sharp, and we can show that. But for the rest of them, we don't have this sharpness. Notice also that the torus has dimension homology up to dimension d, but it's not mentioned here in the theorem. The reason is that if we want the union of the balls to have the d-dimensional homology of the torus, it means that it has to cover the torus. Otherwise, there's always going to be a hole. And to cover the torus, as I told you before, you need much larger radius. So the nr to the d is outside this thermodynamic limit. It has to go like log of n. So it doesn't cover by this theorem. There are other theorems that analyzes what happens then. And as I said before, the main thing that is missing from this theorem at this point is the sharpness, showing that all the 0 and 1 values coincide. But we believe that to be true.
Omer, another question. So in dimensions above 2, your third bullet point says that this one-dimensional homology and this d minus one-dimensional homology appear at different times, at different thresholds. Do you know that lambda 1 is strictly less than lambda 2 is strictly less than lambda 3 is strictly less than lambda 4. It sounds like you don't, but you might conjecture that to be the case.
Yeah, you're true. That's also missing. I mean, we strongly believe that it should be a sharp inequality, but strict. But for now, the best thing we can do is less or equal. You're right.
Very interesting.
And you might see from what I mentioned next why it's only less equal. Okay, so before I tell you a little bit about the method we used to prove this thing, just going back to the TDA motivation I gave you before. So I told you that we know how the death to birth ratio behaves in the noisy cycles, so in the small cycles. And what can we say now that we couldn't say before? So what I told you before is that if we look at the ratio of death and birth among all the noisy cycles, the small ones, then we have a theorem saying that it scales like this log n over log n. What we can do now is if we want to look at the signal cycles, or now we can call them the giant cycles, then we said before the death time is constant. It's just the physical size of the cycle. The birth time, now we know how it scales because we said that n times r to the d is some fixed number. So the birth time scales like n to the minus 1 over d. And now we have at least an estimate for the order of magnitude, which is some power of n. And the nice thing about it is that it tells you that the ratio of death and birth in the true cycle is by orders of magnitude bigger than the noisy ones, which is a positive statement because it says that if you have enough points, you could differentiate between them more easily. Okay, so this is going back to the TDA motivation, and what I want to tell you now is a little bit about the proofs for this statement. So let's start with the appearance of the giant one cycle. So just looking at age 1 and what we might call age 1 percolation. And here, actually, what we need to do is very simple. We just need to go back to the crossing paths. Don't I have a picture? Oh, okay. So I told you before, consider the box, right? We said that we're looking at the torus by placing points inside the box. I told you that if lambda is small enough, there are no crossings and no giant cycles. And if lambda is super critical, we call it, then we have very high probability to cross the box from left to right, from top to bottom, and if it's higher dimension, from every side to every opposite side. Now, how does this help us? So think about this box. And now, I also told you that it doesn't matter what the scaling of the box is. So I'm going to look not at the entire 1 by 1 box, I'm going to take a small rectangle inside it. And inside this rectangle, I know that if I'm super critical, there is a crossing path this way, top to bottom. I'm going to leave that aside, and I'm going to go look at another rectangle. And here as well, I'm past the critical value, so I'm supposed to see another crossing path here. And now, since I'm on the torus, this is also a rectangle. It starts here at the bottom and it wraps around to here. So I also expect to see a top to bottom path here. So far, so good. Still doesn't give me a cycle, but I'm going to play the same game now for this rectangle, but left to right. So I have a left to right path here, I have a left to right path here, and I have a left to right path here. So all of these events, this spaghetti that I just drew, if the value is above the critical value, it must happen with probability going to 1. Another thing that I told you before is that in 2 dimensions, it's sort of clear that everything intersects, but in higher dimension, it's not clear. But we also said that in the box, there is only one giant component. So all these crossing paths actually belong to the same component. So actually, they do connect even if it's in higher dimensions. And now, since they all connect, what I can do is just travel along this spaghetti that I created and generate a one cycle. I can start from the top, go all the way down, come back from the bottom, and then I created a one cycle that goes vertically, and I can also do it horizontally or in any direction that I want to generate all the one cycle that I have in my torus. And that happens with a probability that is going to 1. So the same time that the crossing paths occur, we can also say that the giant one cycle appear as well. And therefore, we conclude that the first threshold, the threshold for H1, is the same as the threshold we have in the classical percolation theory for the giant components. So this is the first part, handling just H1. Now, for handling the other dimensions, we're going to need some kind of a duality statement. And what we're doing is duality between the occupancy and vacancy processes. So I defined, I think, IK before, that the inclusion map, or the map induced by inclusion from the union of the balls to the torus. And I'm going to call it a I bar. That will be, again, the induced map, but for the vacancy process. So I'm looking at the complement of the balls, and I want to ask how cycles here are mapped to the torus. And the duality statement we use is that if I take the rank of IK, namely how many giant cycles I see in the complement, and I add to it the number of giant D minus K cycles that I see in the complement in the vacancy, they sum up to the total number of cycles, which is beta K of the torus. Okay, so it says so here, the giant K cycle in the occupancy process plus the giant D minus K cycles in the vacancy gives me all the cycles that there are. And visually, at least, it may be easier to understand how it happens. So if you think about, this is the three-dimensional torus for me. And if I have a two-cycle here, would mean that I have this blue box, blue square lying inside. So it's a two-dimensional surface floating there with the periodic condition. It's going to be a two-cycle. And if I have this in the occupancy process, then it means that I cannot have this path going from top to bottom in the vacancy. And therefore, if I have this two cycle here, it means that this one cycle cannot appear. And at the same time, if this one cycle appears here, if there is a top to bottom one cycle, it will interfere with the appearance of this surface of this two cycle. So the dimensions are sort of complementing, and every cycle that I see here prevents the appearance of a dual cycle in here. And we're going to use this kind of duality for the analysis that we're going to see next. Okay. I'm going to skip the proof. It basically uses some kind of Alexander duality and a little bit diagram chasing, but I'm a little bit running out of time, so I'll skip the details. Now, so we have this duality telling us that K cycles here prevents D minus K cycles there. How can we use it to continue our journey to say something about this percolation for cycles in dimension bigger than 1? So we're going to start with the top dimension, the D minus 1 cycle at first. And for that, what we're going to do is to look at the complement, the vacancy process. Okay, so this process. And we have the same story, right? We know that if we're subcritical, okay, so if lambda is less than the critical value, then since it's the vacancy, everything works the other way. Then subcriticality means that we have a giant component and we have all the crossing paths. Now, if we have all the crossing paths, we can play the same game I was doing with the spaghetti before. I can create all those paths, glue them together, and create a one cycle. So if lambda is less than lambda bar, then I can say that I have all the one cycles in the vacancy, which means that the rank of I bar 1 is equal to beta 1 of the torus. Now, if I'm using the duality statement, if this is equal to beta 1, then the rank of ID minus 1 must be 0. So if I have all the one cycles in the vacancy, it means that I cannot have any of the D minus 1 cycles in the occupancy. Okay, and so if I'm subcritical, if I'm below lambda bar, then I know that I have no D minus 1 cycles in my process, and the other way around. If the value is too high, it means that in the vacancy, everything is small, which means that the rank of the I bar 1 is 0. I see no giant cycle in the complement. If I see none of them in the complement, I must see all the D minus 1 cycles in the random balls, in the occupancy process. This is again coming from the duality. So now I have all the cycles in dimension D minus 1. So sort of everything changes around the same critical value we had before for the crossing path again. Okay, but now the duality translates the statement from crossing path in the vacancy to D minus 1 cycles in the occupancy. And so the bottom line from that is that the thresh A, that we have a sharp phase transition for the D minus 1 cycle, and the value, the critical value, coincide with that for the continuum percolation for the crossing path. Okay, so so far what we have, we did this gluing thing to prove, to show that we have the one cycles, this phase transition for H1. We use the duality to show that we have the same phase transition for D minus 1. Now we have to handle the intermediate dimensions. So now we want to look at hk between 1 and d minus 1. And to do something about that, what we're going to look is we're going to look at this, I call it a subtorus. I'm going to look at a k-dimensional box lying inside the d-dimensional box, which again, with periodic conditions, give me a k-dimensional torus, which is a subset of my big torus. So I'm going to call that tk0. So I'm just choosing one arbitrarily. And I'm going to look at induced processes. I'm going to take the union of the balls, which are d-dimensional, and intersect them with the k-dimensional torus. So I get, again, another random process inside the lower dimensional structure. And I can also discuss the vacancy and the occupancy here, but now everything is k-dimensional. Now I'm going to define, if you remember in the statement of the theorem, I had two thresholds. They're going to appear now. So lambda k0 is the last time that the probability is 0 to see any giant cycle, or the first time that the probability is non-zero. So that I call lambda k0, and lambda k1 is going to be the first time that the probability becomes 1. So I'm asking when is it, does it stop being 0, and when does it become exactly 1? For now, we don't know to prove that those two values are the same, but we believe they are the same. So this is lambda 0, lambda 1. And now the main thing we want to show is that we have those inequalities that I showed to you before. Right? We know that below lambda 0, by definition, below lambda 0, we have no giant cycles. We know that above lambda 1, just by definition of lambda 1, we have all the giant cycles. If we can show that all of them are in between lambda 1 and lambda d minus 1, then we're sort of done. And if you can order them as well. So I want to show that lambda 0k is less than lambda 0k plus 1, and this, or lambda 1. I want to show this inequalities. So I'm going to start with the following inequality. So I'm looking at lambda 1, and I'm comparing the d-dimensional torus to the d minus 1 dimensional torus. And the point is that if I have a k cycle in the d minus 1 torus, since it's a subset of the d torus, I'm also going to have a k cycle in the bigger torus, in the d-dimensional one. Therefore, if I'm above this threshold for dimension d minus 1, I'm necessarily also above this threshold because I already have those cycles. So I have this inequality if I change the dimension of the torus, but I keep the dimension of homology the same. It goes the opposite direction if I look at the vacancy, the opposite direction. So if I have all the if I have d minus 1 cycles in the dimension d minus 1 in the vacancy, then I have them also in dimension d. So these are just relatively intuitive inequalities. I'm also going to use the duality I had before. So the duality that I had before, if I'm looking at d minus 1 dimensional torus and the k cycles, if I have all of them, then by the duality I had before, it means that I have none of the d minus 1 minus k cycle in the vacancy. Right? If I have all of them here, I can have none of them here. And therefore, the threshold with index 1 here is equal to the threshold with index 0 here. And again, the same I can do with sort of the complement. Okay, so I'm using two things. I'm using the fact that I can include one torus into the other, therefore the threshold follows some inequality. And I'm using the duality lemma that I showed you before, saying that if I have k cycles in the occupancy, I do not have any of them in the vacancy, and vice versa. And all I have to do now is just to connect the dots. So I start with this. So this is the threshold for me to say that I guarantee to see all the k cycles in d dimension. This is less than this. I'm going here. I have an equality. This thing is the same term as here, still inequality, and I end up here. So in the end of the day, what this sequence of equalities and inequalities show is that the threshold for the appearance of all the k cycles in the d-dimensional torus is less or equal to the threshold for appearance of all the k plus 1 cycles in the d-dimensional torus. None of this thing, at this point, we can show that is a strict inequality, therefore we still have to include the possibility of them being equal, but at least there is some nice ordering to them. So first of all, we guarantee to see all the k cycles, and only then we can say that we guarantee to see the k plus 1 giant cycles. And the conclusion of that is that we can indeed order this threshold value, but it's done separately. For lambda 1, we do it separately, and for lambda 0, we can order them separately. we do not know how they interact. And from before, we know that the leftmost end is equal to lambda c, the critical percolation value, and the rightmost one is equal to the one for the vacancy. So this is really in like 3 slides, the main ideas behind the proofs. So basically, we're using a classical result in continuum percolation about the crossing path, and the duality statement, which is more topological, telling us what happens with the interaction between the occupancy and the vacancy, and you just have to sort of combine them all together in a nice way to get this result. Okay, so bottom line, what is the big picture that we have or that we believe we should have? So first of all, the results that we have do not distinguish between the following cases. So if this is the limit, which we sort of want to be between 0 and 1, so we know that for sure. We know that lambda 1 is sharp. We know exactly when it is, when we have the crossing path. So the probability jumps from 0 to 1. Now, for the 2-dimensional cycles, we don't have sharpness. So there is threshold here when the probability is non-zero. There's a threshold 1 here when it's becoming 1. And it could be the case that the next transition happens after. So they are sort of separated, and then only here we start seeing the giant 3 cycles and so on. We also know that at the end, for the top dimensional, we have a sharp result. But this is one option for what can happen. So we have sharpness at the ends, and in between we have ordering, which is in separate phase transitions. But it could also be slightly different. This stays the same, but it could be that they're sort of mixed. So we start seeing the giant 2 cycles, but a little bit after we start seeing the 3 cycles, and the 1 threshold appears after. So there's nothing in the theorem saying that this picture cannot happen. So there is a range where we have a positive probability to see both the 2-dimensional and the 3-dimensional cycles, and only later it becomes 1. So it could be sort of a mixed picture. So these are 2 possibilities that we cannot rule out at the moment, even though we conjecture that it's neither of those, and that actually everything is sharp and all the 0 and 1 sort of coincide. And what we want to prove at the end is that there is a sequence of sharp phase transitions, so that you have nothing at the beginning, then you have the giant 1 cycles, then you have all the giant 2 cycles, then you have all the giant 3 cycles, and it's sort of well separated and happens in a sequential way. We also want to show that there is a strict inequality, which we don't have. So this is sort of the big picture that we have and that we want to have. Okay, so this concludes the main part of this talk. So I told you about this. Our idea was to take this phenomena about giant components from classical percolation theory and see what can be an analog, interesting phenomenon that happens in a higher dimension of homology that is equivalent. We came up with this notion of giant cycles, which are the cycles that belong to the underlying space. And we can show similar phase transitions to the ones known in continuum percolation to those cycles, the appearance of those cycles, which again relates to the question in TDA about when does the big cycles, the important cycles, the true or signal cycles in present homology, what is their birth time? So everything we described here is basically the birth time of the signal cycle. In the remaining, so how much time do I have? It's an hour or less.
Usually it's 50 minutes for the talk, and then like about 10 minutes for questions. But usually.
But feel free to take I'll say take 5 to 10 minutes, and if people need to leave early, that's not a problem.
It's not going to be, I think, more than 5 minutes, but it's still something interesting that so actually the previous results, we're still writing them down, so they're not published. But what I'm going to tell you next, actually, we just recently posted on the archive, and it's some weird connection, or somewhat weird connection, between the Euler characteristic and everything I told you about before. So the Euler characteristic is you can think about it as the alternative sum of the Betti numbers. And the nice thing about it, as opposed to the Betti numbers, is that we, in many models, including the random balls, we can work out an explicit formula to the expected value of the Euler characteristic. For example, if we look at the union of balls, then we can write down this formula. There are some coefficients here, which you might know or not, but we know exactly how it depends on lambda. We can find those coefficients in different cases. And the thing is that if we ask about the expected Betti numbers, like I show you here, this is for the 3-dimensional torus, then we don't have anything explicit to say about them. but we can draw the curve of the, so this is just done by simulation here, but if we draw the curve of the Euler characteristic, as you can see, it tells us quite a lot about the Betti numbers, and it follows those curves whenever each of the Betti number dominates. But for the red curve, we actually have a formula. So we don't have the entire story about the Betti numbers, but sort of we can have a formula for the 0 Betti numbers here because they're more or less equal. Here, this shape is more or less the same as the first Betti number, and so on. So it's an interesting and useful object to work with, the Euler characteristic. And now the observation from this figure is that, so this is in dimension 3, and we have 2 zeros, 2 places where the Euler characteristic is 0. In dimension D, we'll have D minus 1 zeros. And this sort of corresponds to the transition from beta 1 to beta 2. When we have this change, one of them becomes the dominant Betti number. Now let's take this picture, and how does it connect to what I was telling you before? So let's say we're walking in the torus in dimension D, we have this D minus 1 thresholds, zeros of the Euler characteristic curve. In this case, these are 2 points. And before I told you that we have D minus 1 thresholds for this percolation for the giant cycle. And if we run a simulation, we don't have anything analytic, turns out that they are pretty close. So the mu values are the zeros of the Euler characteristic curve, which we can find analytically. Lambda 1, lambda 2 are the same threshold for the appearance of the giant cycles, which I told you about before. And turns out that they appear quite near. And it's somewhat surprising because the Euler characteristic is counting stuff. It's all the Betti numbers together, whereas we're talking about something more qualitative. We expect one cycle to show up. We don't count anything, just this big thing that shows up. And somehow the values appear nearby. So we wanted to ask the question, is there a relationship between these two values? Turns out that we're not the first one to ask it. It's been around in the statistical physics literature for a while, but only for percolation, for the giant components, not anything about homology. And then you don't have so many values. You just have critical, the appearance of the giant cycles and the zero of the Euler characteristic. So this connection is, we didn't make it up, but we wanted to see if it goes higher to higher dimensions as well. So we couldn't say anything analytically about it because we don't know anything analytically about the thresholds. So we just wanted to try simulations. And it's quite surprising, it works quite nicely. So we ran simulations, for example, on the D-dimensional torus. Same scheme I told you about before. I'm generating points in the torus, looking at the union of balls. I can calculate this blue curve, the Euler characteristic. This I have a formula, and this is the estimated thresholds. And you see that they're pretty close to the zeros of the Euler characteristic in dimension 3, in dimension 4, and I think we also did in dimension 5. It keeps happening. It's not always quite exactly on the spot. We don't know if it's a limiting issue or it's something that we stay there, but it seems to be a good approximation for the critical values. Maybe the point is that usually in percolation theory, nobody knows, or people know very little about how to calculate the percolation thresholds. And if we can say that we can get them from the Euler characteristic curve, which you have an analytical formula for, it can be an advantage. Now, to see if this is something that's special about this model, we tried different models as well. So we looked at a completely different percolation model where we have a PERMUTAHEDRAL complex. So in 2 dimensions, I have a grid of hexagons, and I can turn each of them on and off at random. So this is a completely different model, sort of a site percolation if you want. But if this is on the torus, I can do the same thing. And also here I can derive a formula. And we did the same thing. So this is the Euler characteristic curve. These are the thresholds for the appearance of the giant cycles. And again, they appear quite near the zeros of the curves, dimension 3 and 4. So this is, again, a discrete model for site percolation. And an even more different model is we looked at giant Gaussian random fields. So here what we do is we generate a Gaussian function on the D-dimensional torus. And the parameter here is the height function. So we look at we threshold the function at different levels, and we create a filtration this way, the sub-level set or super level set filtration. And we increase or decrease the value, and we want to ask when do we see the giant components. Here also there is a closed form formula to the Euler characteristic curve. This is something called the Gaussian kinematic formula by Robert Aller and Jonathan Taylor. And this is one of the nice things about the Euler characteristic. You can do things, analytical things with it. And again, it keeps happening. So the curves look different, but still they have two zeros here, which are very near the percolation threshold here. And I didn't mention it before, but the yellow point is the appearance of the giant 1 cycle, the green is the appearance of the 2 cycles, and the red is the appearance of the 3 cycle. What we, I think, what we do know for sure that happens is that if the dimension is even and the model is symmetric, like if it's a zero mean Gaussian field, then we can say that for sure the middle dimension will always happen at the middle zero. That will happen, but for the rest of them, we don't really know what happens. So this is actually I didn't put the reference, but it's a paper that's already in the archive. It's just a simulation paper, but we thought it was interesting enough. Yeah, so I'll just conclude. I told you about this percolation phenomenon, this specific model, the random bursts on the flat torus. We said that in continuum percolation, we're studying the giant components, and we extended it to the formation of giant cycles. We saw that there are different phase transitions that for the appearance of different cycles in different dimensions. We can prove certain things, not all of them, but we can show that there's some ordering to the appearance of those cycles. The main thing that we're still missing is the sharpness results. Other than that, there are many different ways to extend this work. One thing that I mentioned is this connection to the Euler characteristic, which is somewhat surprising to us and very interesting to proceed and try to say something more analytically, but that's for the future. So that's all I had. Thank you.
Okay, great, thank you. So questions. So don't forget.
Oh, sorry.
Yeah, no, just wanted to say in general, like you have to unmute yourself so that everyone can hear you.
Can you hear me?
Please continue.
Yeah.
Yes.
You looked at the torus. What about spaces of hyogenous generalizations of those? Did you look at any of those?
No, again, we took just the d-dimensional those. In principle, the methods we're using should not be fundamentally different if you work with other manifolds. But then you might need to change a little bit the definition of a giant cycle because, for example, if you have a manifold that doesn't have two-dimensional homologies and how you define the giant cycle there, we still expect to see something giant formed, but we have to slightly change the definition. And also the technical calculation is going to be much harder. The geometry of things is going to be more technically involved, but it's, as you see, it's appears here. So we don't want to extend it and see exactly what happens, but also you need to change slightly the definition.
Okay, thank you.
No problem.
Other questions for Omer?
Yeah, I can ask a question. So Omer, when you say a giant cycle, it can be really giant, right? And you don't really care about, it has to be in the homology class, but otherwise you don't really care about whether it's big or small.
Yeah,
would it make
it's not,
sense?
Sorry, yeah.
Yeah, so I was
Go ahead,
wondering if it makes any sense or whether this framework could somehow also incorporate within the giant cycles some measure of how giant it is.
Definitely, and I skipped this, but this is one bullet here. I mean, we define giant cycle and this notion of percolation one way. There exists at least one more way or two more definitions for similar phenomena that appear that more related to size, to quantity rather than this, but sort of one of the things that we want to see is what is the relationship between these two or three notions of percolation, whether they still somehow the phase transition are the same or is there some similarity. But definitely there is room to change maybe the definition or think about completely different definitions for what is a giant cycle or what is higher dimensional percolation. This is something that has partly been done, but definitely in the future should be.
Thanks.
Welcome.
Any other questions for Omer? Okay, so if there are no other, so feel free to also ask questions when I stop the recording. But either way, then we wish you happy holidays. I mean, at least the break is starting in the US. Well, for me, on Friday. I'm guessing that for most of you soon as well. And so the next seminar will be after New Year's. And now I would like everyone to unmute themselves so that we can clap for Omer as the last speaker of the semester.
Thank you.
Like other talks will be posted, and thank you for joining.